Welcome to Generative AI Futures. We are diving deep today. Really deep. We're getting into the bedrock of modern AI, the mathematical concepts that allow these huge models to process data that goes way beyond simple images and time series.
Yeah, we're talking about geometric deep learning, or GDL.
And this isn't just, some advanced computer science topic for a niche field. This is the core math that is starting to dictate the structure of the next generation of generative models, of graph-based AI. Basically, everything.
It's truly the essential mathematics that often gets skipped over in standard curricula. These are the concepts that suddenly define whether your multi-billion parameter model converges efficiently or if it actually generalizes to new data.
Right. So if you want to understand why modern AI architectures, the ones working on molecules, physical simulations, or even the really abstract latent spaces of large language models, if you want to know why they perform the way they do.
The answer is right here. It's in the geometry and the symmetry of the data itself.
Exactly. So our mission today is pretty straightforward, but it's intense. We are going to extract the core mathematical concepts that unify what our sources call the zoo of deep learning architectures.
It really is a zoo.
It is. So we're looking for the shortcut, the way to get truly well-informed on the math of GDL, which at its heart is about applying prior, verifiable, knowledge-like physical symmetries directly into the design of a neural network.
And that knowledge is becoming absolutely critical. I mean, we've seen this clear and incredibly rapid convergence towards transformer-based architectures across almost every data modality.
Right.
Language, images, structured data, you name it. But even inside that transformer framework, it's the underlying geometry, the structure of the data, the relationships between the different tokens. That's what dictates success. GDL gives us the formal tools to exploit that structure.
Okay, so let's quickly put this in context for everyone. Deep learning, or DL, this is the field that goes way back to these abstract attempts to replicate biological neurons. I'm thinking of the perceptron, 1957.
Right. And DL uses neural networks with many, many layers. That's the deep part. And machine learning is the broader subfield that's all about the optimization used to train them.
So where does GDL fit in?
GDL is the specialized subfield that focuses on data that doesn't live on a regular grid. We're talking about non-Euclidean structures.
Like graphs, surfaces, abstract manifolds.
Exactly. And crucially, GDL uses symmetry groups as an inductive bias, and that's a really powerful intentional design choice that drastically combats the curse of dimensionality.
Which is vital, especially when you don't have the luxury of, infinite training data.
Which is almost always the case in physical science or drug discovery or any of these high-stakes domains.
So if our goal is to formalize structure, we have to start at the absolute foundation. Let's kick off with part one. The algebraic structures that define and formalize symmetry. This is really the mathematics before you even get to the geometry.
Right, and we have to begin with the most basic structures in all of mathematics, sets and functions. A set is, well, it's just a collection of distinct unordered elements. It's the foundation for everything else we're going to build.
But there's a slight variant on that, which is incredibly important for graph neural networks, or GNNs, and that's the multiset.
Yes, the multiset allows elements to repeat, and they pop up immediately when you're modeling node neighborhoods in GNNs.
Okay, walk me through that.
So when a GNN layer is trying to calculate the new feature vector for a central node, what does it do? It collects the feature vectors of all its immediate neighbors. That collection of neighbor features, that's a multiset.
Because two neighbors could, in theory, have the exact same feature vector.
They could. And more importantly, the aggregation function you use, typically a sum, a mean, or a max, it has to be permutation invariant.
Meaning it can't matter what order you list the neighbors in, the output has to be the same.
Exactly. That's a direct geometric constraint being applied at the most basic algebraic level.
So from sets and multisets, we build up complexity. Next up is the Cartesian product.
This is how we model composite systems. If you take two sets, say $8, their product $$ times B is just the set of all possible ordered pairs, B dollars. In GDL, we use this to construct really complex latent spaces or manifolds.
Example.
For example, you could define points on a high-dimensional hypertorus by combining multiple simple one-spheres. It's how we build these complex structured spaces from very simple components.
And this brings us right to the operational core of deep learning itself, function composition.
Yep. At its heart, DL is just an iterative process. Input goes into layer 1, that output goes into layer 2, and so on until you get the final output. That whole cascade, that's functional composition in action.
We can formalize that, right, for a standard multi-layer perceptron, an MLP.
We can. The function of the entire network, let's call it Fideta, is just a massive composition of these affine transformations. Your weight matrices dollars and biases dollars, and they're interleaved with nonlinear activation functions, sigma.
So the output of one function just becomes the input for the next over and over.
And it's that composition that grants the network its complexity, its universal approximation property. It's what allows it to model these incredibly intricate patterns in the data. The crucial idea here is that the entire architecture defines its own capabilities.
Okay, so the collection of all possible functions that a specific architecture can implement. What do we call that?
That's called the hypothesis class. And our primary goal in GDL is to strategically restrict that hypothesis class by embedding symmetry, either invariance or equivariance.
On. Why restrict it? That seems counterintuitive. Doesn't a bigger unrestricted hypothesis class mean the model is theoretically more powerful?
That's a crucial point. And it brings us directly to the bias-variance trade-off.
Okay.
An unrestricted class, while it might be capable of theoretically fitting any function that's low bias, it results in extremely high variance.
Meaning it just learns the noise and the training data and fails miserably on anything it hasn't seen before.
Precisely. It overfits like crazy. By restricting the class using strong, verifiable geometric priors, like symmetry, you drastically reduce that variance. You're making the space of possible solutions smaller, which makes the optimization problem easier and massively improves generalization, especially when your data is sparse.
So you're trading a tiny bit of theoretical expressive power for huge gains in efficiency and robustness.
That's the game. You're embedding domain knowledge to make the whole learning problem tractable.
That makes perfect sense. And this naturally takes us to the concept that formally dictates symmetry, groups. Which brings us to, really, the historical heart of geometry, the Erlanging program.
A group, which we write as D or dollar, is just a set G or dollar with a binary operation circ that has to satisfy 4 core properties.
Right. Closure, associativity, it has to have an identity element, and every member has to have an inverse.
Yep. The classic physical example is the rotational symmetries of a square, which we call C4 dollars. The set dollars is just the 4 rotations, 90, 780, 270.
And the operation is just combining those rotations. Any combination stays in the set. 0 degrees is the identity, and say 90 degrees is the inverse of 270. It's a closed, self-consistent structure.
And this mathematical formalization, which was championed by Felix Klein's Erlangen program in the late 19th century, proposed that we should approach geometry not by studying shapes themselves,
but by studying the invariance, what stays the same under certain transformations.
Exactly. And GDL adopts that perspective wholesale. We are designing neural networks that are built to respect these natural invariants in the data.
Okay, and this formal approach leads us directly to the 2 concepts that are most critical for designing GDL architectures: invariance and equivariance.
And both of them rely on defining a group action, which is just the formal way of saying how the group YL transforms the input data $6.
Let's start with invariance.
Invariance is when the function's output is completely unchanged by the group action. So winback x dollar is just equal to phi x.
Think of a classification task, like face recognition. The system has to output expert speaker, whether the input image of you is straight on, slightly rotated, a bit to the left.
Right. The feature extraction pipeline has to collapse that entire orbit of transformations down to a single stable feature vector. The orbit is just the set of all the transformed versions of the input.
So the model is effectively averaging or pooling across this whole manifold of transformed data.
It is. Now, contrast that with equivariance. Here, the function's output transforms in a predictable way under the group action. So, ace Cheeto, ace dx, gx equals a jo y, fxx.
Okay, so an example would be a segmentation mask. If I rotate an input image, the segmentation mask of the object in the image should rotate by the exact same amount.
Perfect example. Or think of molecular mechanics. If you rotate a molecule, an equivariant network designed to predict atomic forces must ensure that the output force vectors rotate by the exact same amount.
This feels deeply tied to physics. I'm thinking of Emmy Noether's theorem, that symmetry is fundamentally linked to conservation laws.
It is. In the continuous world, rotational symmetry implies the conservation of angular momentum, and GDL leverages that physical intuition directly. We build architectures by interleaving layers that are designed to be strictly equivariant, They preserve the underlying symmetry.
Which makes the networks both expressive and inherently robust.
And you stack several of these equivariant layers to capture complex, hierarchical patterns, all while preserving that critical structural information. Then, at the very end, you typically perform an invariant operation, like a global pooling or aggregation, to distill all those features into one robust representation for your final task, like classification.
In this design, stacking equivariant layers and ending with an invariant one, it solves a huge scaling problem. If you build in rotational symmetry, you don't need to show the model millions of rotated versions of every object.
No, it inherently understands the rotation group. You save enormous amounts of data and training time. It's the ultimate form of data augmentation because it's mathematically guaranteed, not just heuristically added on.
Okay, that wraps up our algebraic foundation. Now that we've defined structures and symmetry, let's move into part 2. Measuring and optimizing in latent space. We're bringing in the tools of geometry and calculus that power the training process itself.
So we're shifting from these abstract selections and transformations to introducing geometric meaning. We need length, distance, and angle the components for measurement.
We'll start with vectors. They're abstract objects you can scale and add. The way we measure the magnitude of a single vector is with a norm.
A norm, which we write as $, quantifies the magnitude, the length of a vector. The most common one in deep learning is the $2 norm, the Euclidean norm.
And this is the very same magnitude we penalize in weight decay, or L2 regularization.
Exactly. We do that to keep the model's weight small and prevent extreme parameter values, which is a classic way to combat overfitting in these huge models.
So if norms measure the magnitude of one vector, metrics quantify the distance between two elements. So ∆g is just $1.
The standard is Euclidean distance, $2. And you see this everywhere, comparing data points in latent spaces, constructing geometric graphs like k-nearest neighbors for molecular structures. But GDL often deals with more generalized metrics, like Hausdorff distance, which is used to compare complex shapes or point clouds. And in the discrete world of graphs, we heavily rely on graph geodesic distance, the shortest path between two nodes, which is essential for modeling information flow or commute times in a network.
And the inner product adds the crucial concept of angle and similarity.
Yeah.
This is maybe the most fundamental building block of modern transformer architectures.
Oh, absolutely. The inner product, de-Lieb angle, is what defines angles and orthogonality. If the inner product is 0, the vectors are perpendicular. And critically, it induces the norm, because the norm of a vector is just the square root of its inner product with itself.
And this connects directly to the massive LLMs and multimodal models we use every day. Scaled dot product attention relies completely on the inner product.
It does. It uses it to encode the similarity between query and key vectors. It's just a measure of alignment.
And the high-dimensional nature of these latent spaces is key here.
It is. This is where the curse of dimensionality paradoxically becomes a blessing for attention. In these incredibly high-dimensional spaces, like the ones you find in LLM embeddings, random vectors are almost always nearly orthogonal to each other.
Which means the model can pack a massive amount of information into those vectors without constant interference. It promotes a cleaner separation of different semantic concepts.
Right. So the inner product becomes this incredibly powerful yet computationally simple mechanism for calculating semantic relatedness. And we often normalize it to get cosine similarity, which just captures the directional alignment, the semantic content, and makes it stable against variations in the vector's length or norm.
It's robust. It's just the simplest, cheapest way to calculate similarity that respects the geometry of that embedding space.
It is. It is literally the computational engine of attention in those giant multi-billion parameter models.
Incredible. Okay, now let's look at the engine of training. Vector calculus and optimization.
Vector calculus gives us the tools differentiation and integration to describe how fields behave. This is essential for our main goal, minimizing the loss function.
We need concepts like continuity, which just means no abrupt jumps, and differentiability, the rate of change, the ability to approximate a function locally with a tangent line.
But there's a stronger condition, Lipschitz continuity, that's worth elaborating on. It's mathematically vital because it provides a bound on how fast a function can change.
So Fate Bell is less than or equal to some constant $ times 6y.
Exactly. And that bound, Lipschitz constant, is mathematically essential for providing convergence guarantees in our optimization algorithms. If a function is too jumpy, optimization might just overshoot wildly and never converge.
And the heart of optimization is, of course, gradient descent. We define our loss function, $, which is a scalar field over the entire weight space. The gradient, L by LW gal, is a vector field that points in the direction of the steepest increase in loss.
So we just take a step in the opposite direction. The canonical update rule is 1 lie plus 1 equals 1. Let's person in WT, eta L WT, where line is our learning rate. We're just trying to walk downhill on this high-dimensional loss landscape.
But this search is complicated by the curse of optimization. In these non-convex landscapes, finding a global optimum is NP hard. It's computationally intractable.
And this is where GDL loops back in to help. By providing those low-dimensional geometric priors we talked about, by designing the architecture to be locally smooth and structured, we give the optimization process this crucial regularity. It makes the search for a good local minimum much more efficient.
And how do we actually compute that massive gradient across potentially billions of parameters? That's where the chain rule and backpropagation come in, forming the algorithmic core of modern training hardware like GPUs.
Right. A neural network is just a composition of vector fields, 5LR circ FL1, and so on. The chain rule from calculus dictates that the derivative of that whole composition is a product of Jacobian matrices.
And the Jacobian matrix is just the matrix of all the first-order partial derivatives. It's the generalization of the gradient to functions where the input and output are both vectors.
So backpropagation is simply the algorithmic, efficient application of this matrix multiplication. It computes the gradient of the loss with respect to each layer's weights by propagating these Jacobian products backward through the network.
And that backward pass, that massive parallel matrix multiplication, is exactly what GPUs and TPUs are built for.
Precisely. Now, for extremely deep or wide models, computing and storing those Jacobians can still be a bottleneck. So practices like mixed precision training or weight quantization, they're essentially trying to approximate those Jacobian products with lower precision to save memory and time, but without destroying the gradient quality, you need to actually converge.
We've built the foundation and defined how we measure and optimize. Now we're entering the core domain of GDL with part 3, non-Euclidean worlds manifolds and topology.
Manifolds generalize our idea of space to include curved domains. The classic example is the surface of the Earth. It's a 2D surface, but globally, it's curved.
But locally, at any single point, it looks and feels flat. It resembles a Euclidean space.
And we call those local approximations charts. A collection of charts that covers the whole surface is an atlas. This local flatness concept is the key to the manifold hypothesis, which is absolutely crucial for representation learning and generative AI.
The hypothesis states that high-dimensional data, like all possible images of realistic cats, actually lies on a much lower dimensional manifold that's embedded within that massive pixel space.
Yes, most of that huge ambient space is just noise or nonsense. Points on the manifold are the valid data points, the images that actually look like cats. This is why we can encode such complex data using relatively few latent variables in the middle of a model.
And it explains why interpolation works so well in the latent space of generative models like VAEs or diffusion models.
Exactly. If you interpolate linearly between 2 points in the original pixel space, you just get a noisy, blurry fade. But if you navigate along the curved surface of the manifold, what we call a geodesic, the shortest path, you get these smooth, valid transitions, like one face smoothly transforming into another. The model has learned to generate data only on that smooth, coherent surface.
So to handle this curvature properly, we need the tools of differential geometry, specifically Riemannian manifolds.
A Riemannian manifold is a smooth manifold that's equipped with a Riemannian metric, GPI. This is essentially an inner product that's defined on the tangent space at every single point $.
The tangent space, TPMR, is that flat vector space that's just touching the manifold at point $. It's our fundamental local approximation.
Right, and this metric is what allows us to measure distances and angles precisely, even on a curved surface. A central idea in applied GDL is to exploit this local flatness for computation.
How do AI systems handle that efficiently? Sounds complex.
They use 2 fundamental maps, the exponential map and its inverse, the logarithmic map.
Okay, walk us through an optimization process using these maps. Let's take a concrete example.
Let's say we're embedding hierarchical data, like a family tree, into the Poincare ball. It's a non-Euclidean manifold that's really good at modeling trees. Now, when we want to update a point on the manifold, we can't just use standard Euclidean vector addition.
Because the result might fall off the curved surface out of the manifold.
Exactly. So instead, we use the logarithmic map to project the neighboring points from the curved manifold back into the flat tangent space at our current point. In that flat space, we can do our standard, cheap Euclidean gradient calculation. Then we use the exponential map to project the updated point back onto the Poincare ball along a geodesic path.
Ah, so you're preserving the geometric structure while doing all the hard math in a simple, flat space. That's a huge computational leverage.
It is. Now, moving from measurement to pure structure, we get to topology. This is the study of shape and connectivity that's preserved under continuous deformation. People call it rubber sheet geometry.
The classic example, a sphere and a cube are homeomorphic or topologically equivalent because you can deform one into the other without tearing it.
Right. But the surface of a donut, a torus, is not homeomorphic to a sphere because the donut has a hole. It has a non-trivial loop, and you can't get rid of that without cutting. Topology focuses on these topological invariants.
But standard graph models only deal with pairwise relations, nodes, and edges. What happens when we need to model more complex, higher-order structures, like groups of things interacting?
That's where algebraic topology provides the solution, through things called simplicial complexes.
Okay, what are those?
They're a generalization of graphs that include higher dimensional elements. So you have zero simplices, which are nodes, one simplices are edges, but you also have two simplices, which are triangles or faces, and three simplices, which are tetrahedra or solid volumes.
So instead of just modeling who's connected to whom, we can now rigorously model who's connected as a group of three or who is involved in a closed loop.
Precisely. And we use a tool called homology to identify and count these structural features, the topological invariants. H-Shutler counts connected components, H-Delong counts loops or rings, and 2H2 counts voids or cavities.
And the computational tool that unlocks learning on these higher order structures.
That would be the Hodge Laplacian. It's the extension of the graph Laplacian, which we're about to get to these more complex structures. It allows us to analyze signals defined not just on nodes, but on edges, on faces, and so on. It can capture these incredibly complex geometric attributes like flows, cavities, or curls.
This is where the geometric and topological pillars really merge.
Okay.
Let's shift gears and dive into part 4, spectral theory. We're moving into the frequency domain of AI, which is essential for defining things like convolution on irregular data.
Spectral theories study linear operators by analyzing their eigenvalues and eigenfunctions. But to generalize this beyond finite dimensions, we need the tools of functional analysis, which extends vector spaces to infinite dimensions. We're talking about spaces of functions.
Why is this abstract jump so critical for GDL?
Because functions, especially those in Twilio-tobulars, the space of square integrable functions, can be treated as infinite dimensional vectors. The core structure here is the Hilbert space, a complete inner product space. Completeness is the property that ensures things like Fourier series decomposition are well-behaved and always converge.
So in this infinite dimensional setting, spectral theory gives us the framework to decompose linear transformations like the Laplacian operator.
Yes. The decomposition equation is the famous all VV equal lambda Vm. All Y is the operator, all vires is the eigenfunction, and lambda is the eigenvalue. The eigenfunction de Ville maintains its direction under the transformation dollar. It just gets scaled by lambda.
And the spectral theorem is the big result here. It guarantees that this decomposition is clean and complete.
Right. For a certain class of nice operators called compact self-adjoint operators, the Laplacian being the most important example, the theorem guarantees that their eigenfunctions form a complete orthonormal basis for the entire Hilbert space.
Which means you can express any function, any signal in that space as a linear combination of these basis functions.
And that is the fundamental basis for Fourier analysis. Fourier analysis is just the application of the spectral theorem, where the operator is the continuous Laplacian, and the basis functions are the complex exponentials, EEA. It lets you represent any signal in the frequency domain.
Let's connect this to a physical analogy, like solving the heat equation.
The heat equation describes temperature diffusion. When you solve it using Fourier analysis, the solution involves convolution with something called the heat kernel. The heat kernel is the system's impulse response, and it's built directly from the Laplacian's eigenfunctions. It defines how heat, or information, flows and dissipates over time.
So in a GNN, this diffusion process is conceptually analogous to how information is smoothed or propagated across a network.
Exactly. We are generalizing that continuous idea to irregular data structures.
And that generalization brings us directly to spectral graph theory, the backbone of many GNNs.
Graph theory is really the quintessential architecture in GDL. We're dealing with graphs, D, E, E, D, that encode pairwise relations. And the tool of choice is the graph Laplacian. Low dollar is the degree matrix, and E dollars is the adjacency matrix.
What's the geometric meaning of the graph Laplacian in this discrete context?
It's the discrete analog of the continuous Laplacian. Its quadratic form, 6TL LCL, is the graph Dirichlet energy. And this energy measures the smoothness of a vector field 6TLR, the node features that's defined over the graph. Minimizing this energy means you're forcing features on neighboring nodes to be similar.
So it's an implicit homophily assumption baked into the physics of the graph.
It is, and just like in the continuous case, the eigenvectors of the graph Laplacian form the graph Fourier basis.
So the eigenvalues quantify the frequency of their corresponding eigenvectors.
Right. Lower eigenvalues correspond to smooth, slowly varying functions, or low frequencies, across the graph. They represent global features. Higher eigenvalues capture rapid oscillatory variations, high frequencies representing local sharp features.
And this basis allows GDL models to design spectral convolution operators. How does that work?
A standard CNN uses a local filter, like a 3x3 kernel, in the spatial domain. A spectral GNN, however, defines convolution as a multiplication in the frequency domain. It transforms the graph signal into the graph frequency domain using the Laplacian eigenvectors, applies a learned filter to scale the frequencies, and then transforms the signal back.
Which lets the model learn filters that operate globally across the entire graph structure.
Yes, and it serves another crucial purpose, especially in graph transformers: positional encoding.
How so?
The eigenvectors of the graph Laplacian are used as isomorphism invariant positional encodings for the nodes. Since the eigenvalues and eigenvectors are inherent properties of the graph structure, they don't depend on how you arbitrarily label the nodes. By giving each node coordinates based on its eigenvector components, we capture its intrinsic structural role within the graph.
Which is vital, because it breaks the model's permutation invariance in a geometrically meaningful way, allowing it to tell the difference between two nodes that might have the same features but occupy totally different structural positions.
Exactly. That spectral decomposition is doing the heavy lifting for feature smoothing, filtering, and structural encoding.
Let's move to part 5, the cutting edge. We're looking at how researchers are moving beyond static, pairwise graphs to dynamic higher-order networks.
This transition is necessary because current dynamic graph models, which just track nodes and edges over time, have a critical research gap. They are, as our sources put it, axiomatically blind to complex, emergent, higher-order structures.
Okay, give us a detailed analogy. What does that blindness mean in a complex dynamic system?
Okay, consider modeling a sophisticated financial fraud network. A standard GNN can track the flow of money along edges. It might flag a single high-risk transaction, but it will fail to represent the coordinated formation of a group of, say, 3 or 4 shell companies operating as a single unit. That's a 2-simplex, a triangle, or a 3-simplex. This coordination creates a local cavity or a curl that a pairwise model simply cannot detect.
And that group action, that structural signature of fraud, is exactly the higher order feature that's being missed.
It is. The proposed solution is to move to dynamic simplicial neural networks, or SNNs.
This requires transforming the raw time series network data into a sequence of time-varying simplicial complexes.
It's a sequence known as a filtration over time. It meticulously tracks the appearance, the persistence, and the disappearance of these topological features, how triangles and tetrahedra form and then dissolve.
And the engine for processing this complex multidimensional signal isn't the simple graph Laplacian anymore. It's the highly sophisticated Hodge Laplacian.
That's right. The core computational engine for SNNs is the Hodge Laplacian, and it's computed separately for each dimension of the simplicial complex, for the nodes, the edges, the faces, and so on. The key is the Hodge decomposition theorem.
What does that say?
It says that any signal on the complex can be uniquely decomposed into 3 orthogonal components. First, a gradient flow, which are signals arising from a potential, like pressure. Second, a curl component, which are signals that circulate in loops, like traffic in a gridlock. And third, a harmonic component, which are signals trapped within a topological hole or cavity.
So instead of just modeling how features spread, the Hodge Laplacian lets the model differentiate between signal spreading due to a simple gradient versus signal circulation due to a closed loop.
Exactly. It's the difference between water flowing smoothly in a pipe, which is a gradient, and water trapped in a whirlpool, which is a curl or a cavity. This allows the SNN to define incredibly sophisticated message-passing schemes that operate directly on these higher dimensional simplices. It's a fundamental leap in relational modeling.
Okay, so let's connect this cutting-edge research back to what practitioners are more familiar with, the standard GNN and transformer message-passing framework.
The standard GNN layer updates a node's feature vector by aggregating messages from its neighbors. And it relies on a permutation invariant aggregator, like a sum or a mean, to respect the symmetry of that neighborhood.
And transformers, they also fit this framework, right? Even though they were designed for sequences.
Oh, they absolutely do. A transformer performs attentional message passing over what is essentially a complete graph, where every token is connected to every other token in the context window. The attention scores dynamically assign the weights, effectively discovering the optimal graph structure for a given task.
So the oscillation just extends that relational complexity beyond the simple pairs that attention calculates to these higher-order flows and cavities.
Precisely. It gives us a mechanism to encode much, much richer topological information.
This deep dive has spanned from the abstract concept of a set to the absolute cutting edge of dynamic topological AI. Let's synthesize the impact of all these mathematical pillars on modern AI in Part 6.
I think the first major impact is on generative AI and latent spaces. The manifold hypothesis, which is formalized by GDL, underpins the success of all modern generative models. Consider an advanced technique like flow matching.
Flow matching uses these things called normalizing flows to transform a simple Gaussian noise distribution into a really complex target data distribution.
Correct. And this technique relies heavily on differential geometry and vector fields. Flow matching learns a smooth transformation, a flow that is fundamentally a continuous geometrically guided path through the latent space. It uses the math of differential equations to make sure every step along that path stays on or extremely close to the true data manifold.
Which results in exceptionally high-quality, valid samples. The geometry is ensuring the sample quality.
It is. The second major impact involves training massive models efficiently and stably, which brings us to information geometry.
This is where we apply differential geometry tools directly to families of probability distributions. We treat the set of all distributions a model can represent as a statistical manifold.
Yes, and these manifolds come equipped with the Fisher-Rao metric. This metric is the canonical Riemannian metric on that statistical manifold. And crucially, it measures the informational distance between two distributions.
So it's sensitive to how distinguishable two different parameter settings are based on the data they generate. That sounds much better than using standard Euclidean distance in the weight space.
It is. And this math underpins the natural gradient optimization method. Instead of taking a step in the direction of steepest descent in the flat Euclidean parameter space, like standard SGD does, the natural gradient adapts the gradient by accounting for the actual curvature of the probability distribution space.
Why does that matter so much?
Because standard SGD can suffer from really poor scaling. Changing a parameter might barely affect the output distribution in one region, but wildly shift it in another. By respecting the geometry, the natural gradient ensures that a single step size, etadom, always results in a consistent change in the probability distribution, no matter where you are on the manifold.
Which improves stability and convergence speed, especially for these huge models where flat gradients or sharp curvature can lead to really erratic, slow updates.
It's a huge deal for training stability.
And finally, let's touch on the ultimate unifying structure, category theory.
Category theory is the abstract framework that seeks to unify all these different mathematical structures we've discussed: groups, vector spaces, topological spaces. It does that by focusing on objects and the structure-preserving maps between them, which are called morphisms.
How does this highest level of abstraction actually help an AI researcher today?
It provides the tools, functors, morphisms, sheaves, for designing truly large, reusable, and modular ML systems with algebraic rigor. It forces you to define compositional modeling correctly. For example, if you compose two equivariant layers, category theory gives you the blueprint to ensure the resulting function is also guaranteed to be equivariant.
So it's about building modular neural architectures using verified mathematical principles instead of just ad hoc trial and error assembly. That brings us to the end of our deep dive. We started with the simple algebraic concepts of sets and groups, which formalized symmetry. We explored the geometric meaning of norms and inner products, which power attention. We then tackled the curvature of data using manifolds and topology, finding structural invariance with homology.
And we showed how spectral theory generalizes Fourier analysis to irregular data via the graph and Hodge Laplacians, which enables structured learning and the filtering of signals. We saw that GDL's mission is fundamentally about extending deep learning by embedding these geometric priors, leveraging symmetry, and using topological invariance to handle complex, real-world systems.
The key takeaways for any practitioner should be clear. First, the expressive power and generalization capability, the hypothesis class of any AI model, is inherently defined and restricted by its geometric priors. Designing for invariance or equivariance is the difference between a brittle model and a robust one.
Second, the Laplacian, whether it's the graph or the Hodge version, is the critical generalization of the continuous operator. It provides a frequency domain for structured data that is essential for filtering, smoothing, and encoding positional information.
And third, this shift toward geometric and topological pillars is crucial for analyzing complex systems, like dynamic financial or molecular networks, where simple pairwise links are just not enough. The math of Hodge decomposition lets us move beyond simple connectivity and understand flows, curls, and cavities.
The mathematics of GDL is helping us move beyond simply modeling data patterns. It allows us to design models that inherently understand the physics and the relational constraints of the world they're modeling.
Which leads us to our final provocative thought for you to consider. If physics is fundamentally defined as the study of symmetry, as Emmy Noether taught us, how far can geometric deep learning push the boundaries of general intelligence? How far can we get by designing models that inherently understand the deep mathematical rules that govern the very shape and structure of reality, rather than just learning from surface-level examples?